How do we get started? My name is Dean Wampler. Thank you very much for joining us today. Welcome to the very first session of Anyscale Academy, our live events that we're doing this summer. This is an introduction to Ray, and I guess I can move to the next slide here. There we go. It's a way of relatively easily building distributed computing applications, especially in Python. And the purpose of today's tutorial is to show you why that's true, how Ray works, why it's a useful tool for this purpose. We'll get into a little bit some of the ways it's being used in more advanced scenarios like machine learning, but that'll also be a topic for subsequent tutorial events later this summer. So in fact, you can find out more about the events at anyscale.com/events, and I'll talk a little bit about a few of them that are coming up. The first one is June 10th. We're doing a 1-hour Ray Summit Connect event called The Road to Auto ML, The Challenges of Hyperparameter Tuning. We'll have 3 talks by people who are experts in hyperparameter tuning, followed by a panel discussion moderated by me. And you're welcome to sign up for this at the events link at the bottom. The next tutorial event will be on reinforcement learning with Ray RLib, and that'll be June 24th. So it's basically the second Wednesday of the month are the Ray Summit Connect events, and then the fourth Wednesday are tutorial events. So about today's event, Zoom has become a cultural phenomenon. Most of you probably know how to use it already. If you're not familiar with the webinar form of Zoom, which is what we're using, the way you'll interact with us is to use the Q&A feature. We don't have chat enabled, but if you have questions or if you have problems like something's not working in your environment, then use the Q&A feature and we'll try to handle it as quickly as we can. Now, if you do have a problem, all of you should have received an email from us in the last 24 hours with instructions for the links that you'll use to access the tutorial materials. And also a name for the session. It'll be something like academy-user-300 or something. If you have a problem with your session, give us that number or that full name so that we could look at it behind the scenes if necessary. We have some backups as well if we need to give you a new session. But otherwise, anything you put in the Q&A, we'll try to get to as quickly as possible. Now this will be a 2-hour, actually here's an example of those links that you saw. What we're going to do actually is ask you to click the 2 URLs I gave you for the Jupyter Lab. That'll be where all the tutorial material is. And then the Ray dashboard is a tool for visualizing what's going on in your Ray cluster. And we'll use both of those today. That's the only links you should need. I did include the GitHub repo where you can download all of this stuff. I recommend you do that to look at things after the fact. We won't get through everything today. We're going to spend about 2 hours, including some exercises and a break in the middle. But there's a lot more material there that you might want to go through on your own. We will turn off these sessions in the middle of the afternoon, roughly around 3 p.m. Western, Pacific time. So if you want to save anything that you've done, download those notebooks between now and then before we take those off. Someone asked me a question, how do you click on the link? It should just be a link in the email. You should have, if you didn't get an email from us, then let us know in a follow-up question. But you should see, basically I cleaned up the format here, but I took these 3 lines out of the emails that were sent out, and you should be able to click both of these links. So let's see, what's next? Once again, about 3 o'clock today, I'll take all these sessions down, so finish up by then. Like I say, we'll finish in this live session around 2 o'clock, noon. This is new material, and it's a new environment we've built to do live tutorials. If you have problems, then please send us email at academy@anyscale.com. We'd love for you to tweet about the event if you like it. Hopefully, if you like it, but I guess if you want to tweet about what's wrong with it, that's fine too. We're open to criticism. But you can mention one of our 2 Twitter accounts here and use this hashtag if you like. And yes, we'll actually post a video for this tutorial later this week. Watch the blog at anyscale.com for the link. It'll be on our YouTube channel for Anyscale. And the code you can get already. It's on GitHub at this URL. which is also, again, in the email. Okay. Oh, I clicked the link. That's not what I wanted to do. Oh, actually, while I'm there, I guess I should point out that we do actually have, we've already had one Kinect event that was earlier this month with Michael Jordan and Jan Stojka. Really amazing talks and a panel discussion. You can find the links to that, those videos and those slides already if you want. So, okay, so this slide I'll put up when we do an exercise in case someone leaves and comes back to the video and wondering why nothing's going on. So let's actually start the tutorial. Let me close this window. So if you click the link that you got, you should see something that looks like this, probably more like this. You'll see a directory listing on the left, and you'll see, you may not see the overview yet, but if you double click this overview link here at the bottom, you'll bring up this tutorial overview. What you may have seen when you launched it was this launch window, which is kind of busy. But anyway, so this is it. I'll explain a little bit about using Jupyter Notebooks for those of you that have never used them before. That's pretty intuitive once you get the basic idea down. So I'll just work through that a little bit, but I'll assume that most of you have at least played with one of these before. But anyway, let me walk through this a bit so that you know what we're going to do, and you can decide, which sessions might be most interesting for you. So the one that we're going to go through today is the Ray crash course, as we call it. Really, the two first lessons, Ray tasks and Ray actors, are going to be the main focus of the day. These are the core ideas inside Ray for distributed computing, in the case of actors, when you need state. And also, if you have stateless computation, then you use tasks. And we'll see how that works, how it leverages intuitive concepts you already know from Python and other object-oriented languages. And hopefully that will be very compelling for you. I'd like to be able to get through lesson 5 today. I don't know if we'll get that far. Once again, I encourage you to go through these on your own if need be. They're designed to be self-taught. Number 3 is kind of short. It's really just stepping back and looking at, where did Ray come from? Why is it here? What was the motivation for it? Ray multiprocessing goes into ways you can actually leverage Ray today, even if you've already started writing like multi-threaded or multi-processing Python code, some ways that we've created drop-in replacements for popular libraries so that you can break the single node boundary and go to a cluster. Ray Parallel Iterators is a really cool tool for building sort of basic but fast streaming capabilities to process data that's coming in and that's going out and so forth. Then this lesson 6 and lesson 7 we probably won't get into, but they fill in a little bit more background about using Ray that we probably won't get to. What I do encourage you to do, though, especially if you're fast, this time or at least later on your own time, is go through the advanced material, after you finish the basic material. We'll revisit tasks and actors, provide a little bit more depth about how to use them effectively, look at how to profile them and find performance bottlenecks. And then there's also a lesson that walks through the internals of Ray, so you have a better sense of what's going on under the hood. I personally really like to do that with these big systems. I used to do this a lot when I was working with Apache Spark, because it really helps you develop an intuition about what constructs have what effects when you're actually running them, and also helps you debug problems when they crop up. There is some draft material for reinforcement learning. You're certainly welcome to go through these, but these are really rough and will be heavily modified and improved over the next month in preparation for the next session. Okay, let me go back up and see if I have anything else I want to mention. No, let's go ahead and click Ray Tasks. So what you should do is you can just click this Ray Tasks link, or you could open this Ray Crash Course folder and then click 01 Ray Tasks over here. Either one should work, and that'll open up our first lesson. And I'm going to make a little note here. Oops. Okay. Here's our first tutorial, or lesson rather. So a little bit of information about how to use a notebook. So what notebooks do is they sort of mimic the old idea of a lab notebook. All of you probably used these when you were like doing high school chemistry or college chemistry, whatever. You know, it was like graph paper in a notebook, and you would make notes and you would plot lines of stuff that you measured. This is sort of an electronic version of that. It has the idea of cells, which are each of these little blocks. And you can add it, you can put in Markdown for documentation, which you can see here. You can put in code, which is like this particular cell. When you're in a cell and you want to evaluate it, you just, the easiest way, I mean, you can click buttons up here or do like run, things like that. But by far the easiest way is to just use Shift Return. So if you have your mouse in here, or even if you're outside it and you do Shift Return, then it'll evaluate that cell. In this case, it just renders Markdown. Same for this cell. Now I'm at the cell that's labeled number 1. All of the code cells have these numbers on the side. And as you'll see, when I do Shift Return, and I keep saying that so it's easy to remember, you'll see that it's showing a star. It's being evaluated. This is actually importing some library code that I wrote to make it easy to do this exercise, including some graphics libraries. So what I'm going to do quickly is the next 2 cells and then explain what's going on as they run. So Shift Return twice. And what you see here are 3 circles. If I can get this to scroll a little bit. And they're actually updating as they go. And what we're doing is we're actually calculating pi, and you know, the 3.14159 pi. What's going on here? Well, it turns out if I have a square, I have a circle inside it that touches the edges, and I throw random darts at it, and I'm a terrible dart thrower, so that I just go all over the board randomly like this. If you look at the one on the right, you can see that it's slowly filling in the area of the square and the circle. And in fact, it's approximating those 2 areas as it gets, as we throw more and more. We're working up to 100,000 on the right-hand side here. Now, why that's interesting is because this is a way that I can estimate pi. How is that possible? Well, keep in mind that the area of a circle is pi r squared. The area of a square is the side squared. In this case, the side is 2 times the radius, or the diameter of the circle. So basically, the ratio of what's inside, if you do the math, and the math is down here, the ratio of what's inside, the points that land inside versus all of the points, times 4 is equal to pi, and that's right here. So you can, oops, let me just re-render that because it's LaTeX here. If that's confusing, don't worry about it too much, but the point is that the more darts we throw, the more accurate our estimate of pi becomes, and that's sort of the point of this, the exercise that we'll work through in this lesson, is something like this could get really accurate, but we have to throw a lot of these simulated darts at it. In order for that to work, we're going to have to run it in parallel unless we want to wait a long time. So that's why this is an example we'll use. There's a note here that actually a lot of the code here is implemented in Python files right here, like this PyCalc is actually doing most of the heavy lifting. So you can look at these, and a lot of these actually run as standalone programs like this one. So you can play with these outside the notebook if you're not a notebook person. Okay, so anyway, we need to be able to simulate a lot of this stuff, or at least run it in parallel so that we can get to an answer quickly and not have to just wait for a single core to overheat. So let's see how we can do that. And that's the way to do that is to use Ray. So I'm going to go ahead and do some imports here, some utilities that I need as well as Ray. I'm going to define some constants that we'll see in a little bit. And then I'm going to start Ray. Now the way we're going to run it here is it turns out these environments that you're in are already running Ray. And I have this little shell script. It's actually in the Git repo. You can look at it later. But all it's really going to do is check to see if Ray is already running. And if not, it's going to start it running on this machine as a head node. It turns out it's already running, so it's going to say something like Ray's already running, but if it weren't, in fact, if you run this on a laptop, you'll see a longer message about, oh, I just started up, and here's some stuff you should know. All right, so we got it running. That worked okay. That's always a good thing. Now I'm going to actually initialize Ray in this application process, which is the Python interpreter running in this notebook. The two arguments, one, address equals auto says there's a array cluster running, go out and detect it on this node. If it were in some other node, I'd have to give it a URL and a IP address, rather, and a port number. And then the second argument, ignore reinit error. The only reason that's here is because if I want to reevaluate these notebook cells, which you can easily do, I can come up here and just do this again if I want. This means that I can do this one over and it won't complain excessively. So that's the only reason that argument's there. You can see it printed some nice information like the local IP address. There's something called the object store that we'll explore a little bit later on. And also this next thing that I'll mention, which is this dashboard URL. So if you evaluate this, this URL is not going to work for you. And the reason is because it's pointing to localhost. And that's why we gave you the second URL, which is this dashboard URL. You can see the address up here for me is much different than the localhost version. If you're running this tutorial on a laptop, then you'll want to use this link. You click it, it takes you to what you want. Actually, if I click this now, it's going to take me to this dashboard, which does happen to be running on my local machine. But for your purposes, don't bother clicking this. Click the other link I emailed you that gives you this view. And what you can see here, by the way, we'll come back and look at this a few times, but for right now, it's showing me basically the CPU utilization, the RAM, and so forth on this particular Amazon virtual image. And I have two array processes that are idle at the moment. They're not doing anything. We'll make them do something here shortly. All right. Now let's actually write a little function that's smaller than that pi_calc program I showed you a minute ago. This is a way of estimating pi using NumPy. Let me evaluate this to define it. Let me just give you the gist of what's going on here. If you've never used NumPy, this won't make any sense to you, but it's actually pretty clever what's going on. Now I need an x and y coordinates to be random. Somebody asked, I'll just go ahead and answer this. Is it safe to deploy inside a Docker container? Yeah, and it looks like Bill is going to provide another answer too. But yeah, the short answer is yes, you can do this. We're even working on making this easier, in fact. Okay, so to estimate pi, I'm going to do this trick. I need random points in the x coordinates and in the y coordinates. And I'm going to have like an xy point that's all over this square that we had before. So that's what I'm going to do here. I'm going to generate some number of these random points between -1 and +1. So I picked radius of 1 for the circle. What this line does is it actually turns it into xy tuples. So it's sort of analogous to Python's zip method. Now, what this thing is doing, it's actually creating, it's either setting up indices or the equivalent of a predicate. This will be used as an index into the array I just created, XYS. What it will do is it will select all of the points that are inside the circle. So notice the expression here. I'm basically multiplying the two vectors together, effectively squaring them, and then asking, is that distance less than 1? And then when I do use this as a query, so inside inside the argument list for XYS, that's going to actually return all of the points that are inside the circle. And all I really care about is just the number of them. So, so that's what this is going to calculate for me. The shape basically gives me how big the array is, and shape 0 picks the one coordinate I care about. They're actually the same, x and y. So here's that formula I mentioned before. 4 times the number of points inside the circle versus the total number of samples, and that's my approximate value for pi. Okay. If you didn't follow all that, not a big deal, but it's kind of a cool little way to express this idea in a concise way. NumPy is kind of amazing in that way. So we've already evaluated this, so let's try it out. Now this may take a little while because these are relatively lightweight virtual machines we're running on. I'm going to run it for these values of n. This format string is just for printing out results, and here I'll try it, and I'll actually time how long it takes. And let's see how it goes. You can see from a previous run, it'll be roughly 20 seconds or so for the last run where we're calculating at 10 million points. And it gets slower as it goes, but notice the value for pi, the standard deviation we're averaging over 20 of these calculations. So we're doing like 10 million 20 times, averaging over that, taking the standard deviation, how much do they vary? And then the error is how accurate our mean is versus the real value of pi. As you might expect, this one is a very unusually accurate number right here. That's quite accidental, but most of the time you just see a decreasing error size as we get to bigger values of n, and they average over 20 of them. And just for grins, let's see how that trial business matters. Like if I average over 5, is it less accurate than if I average over 20? As you might imagine, effectively it is. So what we're really doing here for this one, for example, is we're actually using 70 million points effectively to calculate pi. And so the number is going to get progressively better with some fluctuation that's typical of a statistical process. We'll actually graph this data shortly so you can see what it looks like. But the main point is that the larger value of n does give us more accurate results, but it takes a lot longer. And if we really wanted to get out to, let's say 100 digits of pi, that would take forever because we'd be up in the billions or trillions of points at that point. You'd probably use another algorithm to calculate pi if you really wanted to do it to that accuracy. But let's look at this over here too. So if you look at the dashboard, what you notice is this is the CPU utilization right now. It's basically nearly maxed out. There's it's not completely maxed out because there's a lot of other stuff going on. The Ray tasks are idle because we're not using Ray at the moment. And this is almost done. What we'll see in a minute, though, is that those Ray tasks will get hot when we do this with Ray, and we'll see better utilization overall. And it's especially noticeable on a real machine and not just a small virtual machine. Okay. Now let's see how we turn a normal Python function into a Ray task. And that's the term we use in Ray is task. What we tried to do in Ray is to take familiar ideas and extend them to be distributed without introducing a lot of new complications that maybe go beyond what you really care about. We know how to write functions like this estimate pi function. We're kind of used to doing that stuff. Notice it was a stateful thing. I just passed in all the information it needed, and when it was done, it forgot everything. We'll come back to stateful in the next lesson. To turn this into a Ray task, all we have to do is define a function and give it this decorator at ray.remote. And in this case, all I'm going to do is simply call the other one. So I have both, like my cake and I can eat it too sort of thing. I've got the original function I can still use, but now I have this Ray task I can use. It basically does the same calculation. So let's just try it and see what it returns. And notice that the way you call a task is instead of saying, Ray estimate pi argument list, it's Ray estimate pi.remote argument list. Now Python's pretty malleable. We could have not required that remote function, but it's actually really good documentation when you're reading code. You can very quickly tell what's calling and using Ray versus what's just regular Python stuff. So it's a little bit more stuff to modify if you want to change code to use Ray that isn't using it. But it's worth it for that sort of long-term readability and documentation. Notice what it said it returned. It returned some object ID, and it came back really quickly. You probably didn't notice, but it actually finished very fast. This object ID is actually a future because we've started an asynchronous task running in our cluster, and this future is how we get the value when that task is finished. And the way we get that is this method called ray.get. And as you can see, if we estimate pi with just 100 points, you get a really bad estimate. But you call ray.get to actually fetch the value. Now, one thing that isn't covered in the lessons we'll talk about today, and I'm just going to add this right now to show you what it's like. But if you do, I'm going to add a cell using the hotkeys. So there we go. I just added a code cell. You can do that up here if you want. I think it's under Edit. You can add cells. But I use notebooks all the time, so the hotkeys are pretty quick to learn. If you really want to know what they are, I did escape. If I was here, I did escape to get out of the edit mode. Then I did B to add a new cell, and then Enter to actually edit the cell. Anyway, what I was going to show you is there's also array.put. So if you have an object you want to put in this distributed object store that's behind the scenes on all the nodes of the cluster, you can do that. And what I'll do is I'll just put, some string like so. If I print, actually, let me do this. I'll just print foo here. Whoops, I can't type. Really can't type. It's another object ID. Now I used A to add a cell before the one I was in, and now I can do ray.get again. So if I do ray.get foo, I get the object back. So there is actually a way to put stuff in what's called the object store if you want. There's a lot of details in the advanced material about this object store idea. All right. So let's try this with just increasingly large numbers of points. And you can see that I can do a list comprehension where I just iterate over these three ends, call a array estimate pi remote on each of those, and then call ray.get on the list of IDs. So you can either pass a single ID for the future, or you can pass a list of them, and then it returns a list of the answers. Okay, let's try, we had this try it function up here. Let's write a array version of it. So let me walk through this quickly to talk about what's different. So I'm going to do that trick I just showed you with the list comprehension. Someone says, give me 5 trials. So I'm going to do for some counter up to the range of 5, 0 through 4 actually. I'm going to call this my new array estimate pi function on that. That'll give me a list of IDs. Now these are going to fire off asynchronously. If I was on a real cluster and not a small virtual machine, they would all be running in parallel, just grabbing whatever cores they needed. And then I can call ray.get to retrieve all of them at once. We're going to refine this idiom a little bit later, but that's an important thing to note here is that when you're calling something.remote, ideally you're firing off an asynchronous task so you can continue to do other work. There are cases where that doesn't work, where you actually do have to be synchronous. But if I just did like ray.get on the thing that I just called ray estimate pi, then I would just synchronously walk through one at a time and not do them all in parallel. So that's a key point here. Fire them all off at once and then come back and get them when they're ready is what we're doing. Then we'll do some statistics that we saw earlier that I didn't really talk about, but we'll calculate the mean over these trials, the standard deviation, how long this all took, and then we'll print the results. So pretty much like we saw before. So now if we run this for the ray case of increasingly large n, but for trials equal 20, trials is a variable that was set in an earlier cell. Let's wait for this to finish, and I'll go ahead and start the next one. The next one just does the same test of what if we change the number of trials. Okay, so that took 15 seconds. If I scroll back to what it was before, it was 16. Not too great, but we're also on a really small virtual machine. Let me see if I have this on my laptop still. Yeah, on my laptop, so it was 9 seconds before on like a 4-core laptop. And then it was like 5 seconds, almost half as long running with Ray, because I now could go in a parallelism of 4 instead of what we have here, which is 2. Let me go back to this. I'm going to run this one more time so we can actually look at the dashboard. So let's go over to the dashboard. And what you can see is now I've got these 2 Ray tasks are, basically, they're not completely utilized, but at least I'm getting more parallelism now. So I'm doing basically twice the work in the same amount of time. Whereas when I was running that over here, it was more like 5 or 6 to 8 sometimes. All right, let's see. Oh, I clicked the wrong one actually. I clicked the original one. All right, so the last thing we'll do in this section is we'll actually plot this. Now I have to wait for this to finish. It's getting there. But I'll go ahead and start evaluating these cells. So we've got all this data. It's kind of hard to just read numbers. Let's actually plot things. So to do that, I'm going to use NumPy arrays. That'll be more convenient to work with them when we do this plotting. I'm going to use Bokeh, which is a really nice plotting library. And here's a plot of the no ray versus ray times. Now you can see it's not that different. Here's another run. Most of the cases, I wanted to assume that you didn't necessarily get the Boca to work for whatever reason on your machine. So most of these graphs also have static images you can click. And in this previous run, in a more realistic compute scenario, you can see that Ray had a much slower growth curve. In other words, it performed much faster as we scaled up N versus not using Ray, where we were really pegged to one core on our machine. So let me close that. If we do a log-log plot, we can see the lower end behavior a little more easily. If you're not that familiar with log-log plots, don't worry about it for right now, but it's a nice way to compress exponential growth. Here's a previous run. You can see that now, in fact, what happens when you see a line in a log plot is you're actually seeing exponential growth or inverse exponential growth flattened. So it's a little bit easier to like calculate slopes and stuff like that. But the general rule is that the overhead of Ray, the performance benefit of Ray is actually better consistently over this whole range than it is for just running in a single process. Okay. Let's do a couple more plots. This is the case of running different trials, but 10 million nodes. And you can see they're roughly the same. Here, in a real machine, the performance is much better with Ray versus not using Ray. So we can scale to much bigger N is the point here without running out of patience or running out of compute resources. And then the last one is two pairs where we're actually going to show the errors and the improvement as we got to large N. So what is this showing? Well, when I only have 1,000 points, 10,000 points, 10 to the 4, I have a lot of range in my standard deviation. The errors are pretty big and the average is way off. But as I get to larger and larger N, the errors converge down and the mean converges down to the right value. So you can see down here, it's pretty close to the correct value, at least, for some level of close, I guess. Now, if I plot this for Ray, the plot is pretty much the same because all Ray has done is give us faster performance, but it hasn't actually done any better calculation. So this plot, conceptually looks the same as this one, although the details vary a little bit. Okay, let me pause for a second. Any questions anybody has? You can put them in the Q&A feature. I know I've blasted through a lot of stuff here, but hopefully you get the gist. I'm using Ray when I have something that I can really run a lot in parallel that doesn't have to be synchronous. I can turn those into Ray tasks and then run it. Okay, no questions at the moment, so let's keep going then. And we're almost at an exercise. And that'll be our first chance for a break as well. Recall that I said a minute ago that you want to fire off all this asynchronous stuff, and then you want to ask for the results with ray.get. But there's actually a slightly more nuanced way to do this that's preferred, and it's illustrated with this example, where I have this new function. Let me just take this question that somebody asked. Does Ray task work with any library, e.g. pandas? It does. There's actually some really nice integrations that people have been working on with pandas. You might Google Modin, M-O-D-I-N, which is a research project that's very similar. Yeah, basically Ray is just a library, and it has this behind-the-scenes object graph where you can stuff things and then pull them out of use them in other tasks or actors anywhere in the cluster. So in fact, it's pretty opaque and pretty agnostic to whether it's pandas or NumPy or any of that stuff. So that works pretty well. And in fact, we're actually using part of the pandas. Sorry, I'm confusing it with something else. Never mind. But pandas does actually work pretty nicely with Ray. Okay. Sorry, let me click something here. There we go. All right, so this function here, just to keep it simple, what I'm going to do is pass in some n which is going to estimate pi again for some value, for some number of n, but then it's also going to sleep for some period of time. So what we're going to illustrate is what happens when you have tasks that take a long time versus take a short amount of time. Oops. So if I click this, there we go. What I want you to observe next, well, let me just explain this code, and then I'll ask you to watch what happens next. But so here's a line that's very similar to what we saw before, where I want to fire off all of these asynchronous things at once. It's a little bit more complicated the way I wrote it than before, but it's basically the same idea. Just fire off as much as you can in parallel all at once. Now, previously, I had something like ray.get right here on those IDs to pull it all back at once. The problem is the way we've set this up is that some of these things are going to finish quickly and some will take longer to run. Excuse me. That sucks. What I really want to be able to do is as soon as work is done, I want to process it while other work is continuing to run. And then when that's done, I want to come back and grab it. That's where ray.wait comes in. So what we have is this idiom where we set up a loop that's going to loop over the IDs of tasks that are still running. And I initialize that right here, basically using the Python list. All the IDs, I'll start with that as the list I want to query. Then I'm going to call this method ray.wait on that list. And what it returns is two lists. First, and it's basically a bifurcated a partition of the original list, the things that finished and the things that are still running. And that still running is my loop variable. So I'm going to iterate through this until there's none left. Everything is finished. Now, the way I've written this is it will return as soon as one of these tasks is finished. There's arguments you can pass to say, oh, I'd actually like to wait for two at a time. There's also a very important argument for setting a timeout that you'd want to put in production code so you don't deadlock in case something just gone really bad. But for right now, for simplicity, we're just going to wait as long as it takes for the first one to finish. This is a blocking call. And then, so what we'll find actually is this finish is always has one element. And then we'll process that. So we call ray.get on that list of finished stuff, print out that, and then loop until everything's done. So that's what this is doing. So what you'll notice is that every 2 seconds we're going to get output because we're going to take 2 seconds, 4 seconds, and 6 seconds to do this work. And actually, it's a little longer than that, but the point is that every 2 seconds or so, the cumulative time is a little bit longer because we're actually doing several things. But every 2 seconds or so, we get results back. Okay. The advanced material explores this a little bit more, including those options that I mentioned. But the key takeaway here is use this idiom in production code so that you get results as quickly as they're available, and you can process those results while other things are still running. Okay, so what we'll do is we'll take about 15 minutes to work through this exercise. And I think actually number 3 is probably the easiest. And that is you'll basically take the graphs that we did up here, like these graphs, and run them for smaller n. The purpose being to see if there's a point where ray and non-ray cross. That's probably the easiest one to do. You just basically change some numbers up above. Another one you could try though is this one, although this can be kind of expensive to run, especially on these nodes. But the idea is, how far do I have to go in n value till I get an accuracy of 3.14 or 1.5, rounding up from 1/4 time. That one might take a while to run. This one's probably slightly harder, and that is that there's a slight flaw in the way that we implemented estimated pi. And that's, where was that? Oh yes, it's right here. As n gets bigger, I'm going to create bigger and bigger arrays, and I could eventually run out of memory. But because all of these points are actually independent, I don't actually need to do all at once. I could do 10 at a time or 100 at a time or whatever. And so the point of the first exercise is modify this code so that for some number bigger than, let's say, 100,000, I'll just do chunks at a time and then aggregate the results so that I don't risk running out of memory with having a number that's too big and an array that's too big. Because notice, I basically threw away this array after this point. I don't really need all this information anymore, so I can do it in a smaller way. Okay, so why don't you, excuse me, take 15 minutes or so, take a break if you want, and we'll come back at on the hour at 11 o'clock. And I'll be here if anyone has questions. If you have any issues, let us know. And otherwise, I'll just put, where did it go? This, that we're doing an exercise. So if anybody comes in, they'll see that, we're actually in the middle of the video. All right, everyone, starting again. If anyone can't hear me, put something in the Q&A, but hopefully we're back. I was on mute for a second. Someone says there's an echo. Hopefully that'll go away in a second. Okay. So here's what we're going to do. We're running a little bit behind, so I'm not going to go through the solutions, but I put all the solutions in this notebook here. There's a directory called solutions on the left, and then inside is one notebook that has all the solutions. So take a look at those if you want to learn more about it. This has all the solutions for the whole tutorial, actually, including the lessons we won't get to. So let's go on to array actors. You can click that either here on the left, or you could go back to this overview notebook and click array actors here. I'm going to go ahead and close this. Oops. So here, I just did something you don't want to do. It's annoying. I did Command W, which will try to close the entire Jupyter UI. I'm just used to doing that with browser tabs. Fortunately, it reminded me that I really don't want to do that. Not a big crisis, but it's kind of annoying. Anyway, let me close this with this button. And I'll close these just to clean up a bit. And we're done with the tasks. So now we're back to the actors. Okay, what we learned so far is how to parallelize stateless work, like functions where you pass in everything the function needs and you return it. Now, certainly we could do something like make a database call, do an RPC request, whatever inside. That's up to you if when you need it. But what if you have bits of state that you'd like to manage, but in a distributed way? The idea behind actors, and I'll explain the word actor in a second, is that it's going to leverage an idea that we already really know and are comfortable with, which is the class. If you declare a class, it's usually intended to hold some state to give you ways of manipulating that state and retrieving it, and that's what we're going to leverage. And the example we're going to use is Conway's Game of Life, which you've all seen these diagrams of this game. I'm very sad to report that John Conway, who created this, actually died of COVID-19 about a month ago. But he was about 75, I think. All right, so let's do some imports again. I have a lot of this code in some libraries. This gameoflife.py file is where a lot of the code is located. I'm going to give you the gist of it, but it can get kind of complicated when you get into some more advanced stuff. So I just put it in a library. We're going to import some graphics utilities again because we want to plot this thing. So this is actually just an animated GIF that you're looking at up here. We're actually going to plot live games in a minute. And basically I have three classes. The first one is something called the state. That's just going to be a placeholder for my n by n grid. I'm using square grids. There's really no reason they can't be rectangular, but for simplicity, I'm using a square grid. So we'll initialize the grid. For simplicity, we'll initialize it with random values, either 0 or 1 to be on or off, alive or dead. And then this living cells function actually just returns key value pairs for the coordinates of the living cells. This is actually useful for the graphing library. Won't have a lot of time to go into that, but the graphing is in this actor less than util.python file. If you want to see how I actually did these live graphs, it's actually not easy in Jupyter to do live graphs like we're doing, so it took a while to figure out. Okay, for time's sake, I won't go through all the rules. There's 4 rules for deciding whether a cell will live or die in the next generation. It's based on its neighbors. Here's the 4 rules if you want to look at that. but let's just take this as a given for right now so that we can move on. And I have a class that's going to encapsulate that, where it'll copy the grid to create a new grid, and then it will apply the rules for each cell in that grid to compute a new grid, and then it'll return a new state object that represents the new state of the game. And then finally, there's a game class that just sort of encapsulates the initial state. It's going to actually keep a list of the states, so we could go back and look at the history if we wanted. And then you'll actually give it a rules engine. The reason I'm passing in rules here and made this a separate class, the exercises actually get into optimizing this, where you might want to change out the rules with more advanced implementations for performance. All right, if we try this, we have a little function that's going to create a new game. So what it does is it creates an initial state, Conway's rules object, and then constructs a game with it and returns it. Pretty straightforward. And there's actually there's a method in game that prints, I think it's in game, maybe I put it in state, I forget now, but it prints out this ASCII version of the state of the game that looks a little bit more like what you would expect to see when you actually plot these. Here's a helper routine that creates this graph. It's empty now because I haven't started running the game yet, but this will be the graph that is live as we update things. And here's a function that's actually going to do this. So we'll use this trial function a lot, where we can have more than one game. We'll see why in a minute. The graphs is just really the hook to this thing up here. How many steps we want to take, basically how many steps in the life of the whole game. Batch size, I'll get back to that in a little bit later. And then some other things. So also pause between batches at the end. So it looks more realistic. We'll actually sleep for 0.1 second between each life cycle of the game. So it looks more like a typical game of life display. And now we'll run this, and you can see you get this nice display of the things evolving. Notice we have some stasis points. They'll eventually get cannibalized when something comes near them. It's a lot of fun to watch these things, and it goes for 50 steps, so it's already done. You could rerun this if you want it. Actually, it recreates the game, so it's not as interesting to just keep going, but you could try modifying this code so it can take an existing game and keep evolving it. All right, if we look at the time, so this was one game. We took 50 steps, batch size is 1, come back to that later, and it took us about 10.5 seconds to do that. So one thing you should ask yourself right away is, where did that 10 seconds come from? I said that we're going to sleep for 0.1 seconds between steps, and we had 50 of them, so we slept for 5 seconds. If you look at the numbers here, it took about 5 seconds, almost 5.5 of actual compute time for the user space and total, and the wall time was 10.5 seconds, so that's where the other 5 seconds went, was sleeping between these steps. Well, let's suppose we wanted to run a lot of these. Let me just get this started, and watch what happens. Watch the behavior. It might be a little jittery on Zoom, but when you run this locally, watch what happens with these games. You basically see this wave effect as the games are updated, and the reason is this is all running in one thread. If I go over here to the dashboard, there really is only 2 cores on this machine, but I'm only using half of the CPU because I'm only using 1 core, and it's running hot because everything is being done in a single thread for this update. And I get this wave effect because it's actually only doing 1 game at a time. So it's not terribly good. It doesn't look right. And it's also inefficient because I'm not leveraging all the cores on my machine or in my cluster, even though I'm doing something that's highly parallelizable. Now, the reason I set up this example of running lots of games, well, it's kind of cool to look at, but when you get into something like reinforcement learning, where you're maybe trying to train an agent to win, like an Atari game, you're going to want to play a lot, and ideally do that in parallel so that you train this thing in parallel, this agent, to get good at the game. So that's a scenario where you might want this extreme parallelism as an option. Okay, let's see what happens if we do this with Ray. And first, let's look at the time here. So this was about 18 user seconds, 23 wall seconds. Actually, again, 5 seconds sleep between each step. We'll use the same script to check that Ray is running. It's already running. We'll initialize it like we did before. That is, initialize Ray in our process. As I mentioned, this URL only works if you're running on a laptop. You already have the array dashboard. So let's talk about actors. Where did this name come from in the first place? This is actually an old concurrency paradigm. It goes back about 50 years. It was invented in the 70s. I'm blanking on the name of the guy who invented it. Anyway, but it's a really intuitive model. The idea is I have these autonomous agents or actors in my world, and I'm going to send them messages to do work. And each of them will do that work in a thread-safe way. That's what the actor system has to give me. So I don't have to think about multi-threaded programming or all of that stuff. I just have this intuitive sense of making a request or sending a command to some agent that will do those things in the order received, and then maybe send a result back to me. So it's a very concise, reasonably intuitive concurrency model. It's been used in a lot of systems. So that's where the word comes from. That's why we're using it. But the association with what we know is that if we already have this idea of keeping state in a class, so why don't we just make a state into this distributed actor that can run anywhere in the cluster, and then it's got state that it's managing. I can reach that state from anywhere in the cluster where I need it. And I can do all this in a thread-safe way. And one way to do this in Ray is to just subclass the original actor, or sorry, the original class. So I have this non-Ray game class. All I need to do is use the same @Ray remote annotation or decorator, declare a new class that subclasses game. I have to pass constructor arguments. Now, one difference with actors is, excuse me, I get choked up when I talk about this stuff. One difference with actors is you can't reach in and get state out of the object like you can in regular Python. You have to have a getter method. So that's what these two methods are for, to retrieve these objects that normally we would just grab right out of the instance. Now to construct these things, we use, instead of Ray game and then argument list, it's Ray game.remote like before. So it's very much analogous to the way tasks work. So really the only difference right now is that we're treating just the game as an actor. We're not even going to use an actor for the Conway's rules or for the state. The state actually doesn't make any sense as an actor because it's actually, the way we're using it, the states are immutable objects. They're just values that we just pass around. So it's not actually that beneficial to make them an actor. That would actually add extra overhead for the communications. We will see that there are uses for turning Conway's rules into actors, or at least using actors inside them. But for now, we'll just not do that. We'll just keep it simple. Our game is an actor. That will make it easier for us to run games in parallel, where each game will just be cranking on a core and doing all that in parallel. All right, so that's how we create one. This is the way that we'll try it. Basically, it calls this new game function, and then I have it print out the first two states, or walk one state and then print it out, just so we see what it looks like. And if you eyeball it carefully, you could see hopefully that the rules are properly evaluated, and this state really is logically after that state. All right, let me just recap the rules for actors. So you take a regular class and annotate it with ray.remote. All of the accessor methods have to be added where you want to retrieve state, because you can't just reach into the instance. You use .remote to construct instances. You use .remote to call methods on them, like do the next step of the game. And then, as before, we're going to use ray.get and ray.wait to retrieve values. All of these remote calls, once again, they're asynchronous. Well, with the exception of this, I'll come back to that. This one. So we need to use ray.get to actually return the values. Now, the difference with a constructor, it actually returns the actor immediately, but the object is off somewhere in the cluster somewhere. So it's still sort of the same idea of being a hook for remote work. Okay, let's run our trial again, this time using Ray for this grid. And I'll start it and watch how it behaves this time. So you may see these warnings that I'm seeing. We're on a really small machine. We're really pushing a lot of Python tasks onto these two cores I have. So we start getting warnings like this. In a real cluster, you're much less likely to see this, but you could also auto-scale in a real cluster to get rid of them. What you should see, though, is that these games are now updating independently. It doesn't look like we have this wave phenomenon anymore. They're just at random on their own, updating in parallel. It's a much more visually appealing display, if that's what we care about. But it also means that we're leveraging our cores more in parallel. So to actually explore this just a little bit more, let's evaluate these cells. So this is a way you can actually ask Ray, how many cluster cores do I have? I can get the cluster resources, and then it actually returns a map, and then I can just ask for the number of CPUs out of that. On these small instances, it's 2. I don't actually have this notebook running over here. Actually, maybe I do. So on my laptop, I switched to my laptop view. Let me see if I can find that. Yeah, I have the equivalent of 8 logical hardware threads, basically. This is really the same as the number of workers. These are the separate processes that Ray starts to do work. I have 8 on my laptop. I have 2 on this machine over here that we're looking at. Okay, let's try this. Now what we're doing is we're going to run without any pauses between batches so that we get rid of that overhead that obscures performance. We've run on 50 steps again. This time we ran 2 games, and I'm looking at this output, and it took 8 seconds. Now this is the non-Ray version. Now if we try Ray, actually let me run this again, and while it's running, let's look at the dashboard again. And what you can see is that one of the Ray processes died. That'll be restarted, but it's basically using one of the cores at most. It's not really getting me much parallelism. And now that's dropped back to a few percent, it's basically done. That took 7 seconds. It was about 8 seconds before. Now, if I run the Ray version and switch to the dashboard, now I can see the process is running. It actually started new ones. You can see that it's showing you what actor it's running at the moment. And so I'm getting much more utilization. It got up to close to 100% utilization right there. And it finished actually slower. Now, unfortunately, again, these are small instances, and sometimes the numbers are a bit deceiving compared to something that's a little bit more realistic like a laptop. If I run these same trials on my laptop and I used much bigger runs, then I was getting basically like a 2x performance improvement, 23 on this particular configured run, and about 10 on this one. These are much bigger runs, actually. Okay. We'll come back to that in just a second, a little bit more about this, but let me fill in a few more details about actors that you might want to know. When we spawned those tasks in the last lesson, because they were stateless, as soon as the task was finished, then Ray could garbage collect it and remove it. Now, there's a little bit of sophistication that I'm kind of glossing over here, but basically it's sort of a fire, forget, and dispose of when you're done kind of scenario. But because actors are holding state, they're actually pinned in a worker, and they're going to be held there until the reference to them disappears from all the Python code that's running. So just as regular objects in Python are garbage collected when they go out of scope, the same thing happens with actors, that they'll be garbage collected when they're no longer needed. But they are pinned in memory because somebody who's holding a reference to that actor might need to get to that state. Now, another important point to know is that I said it's holding state. It's somewhere in memory in the cluster. This is not durable state. If that node goes down, you will lose that actor. Now, there are semantics, definitions you can provide about restarting actors. We get into those in some of the more advanced materials. But if you really care about durability of that state that you're updating, then you'll have to add something like a database write that periodically flushes to disk or something like that, whatever makes logical sense for your application. Someone's asking the question here, does Ray have the notion of persisting and restoring actor state to enable long-running actors to resume computation? Not specifically, not at a fine-grained level. There are some features for checkpointing, especially in some of the more advanced libraries, but as a rule, it's not built in. Some of my colleagues might want to answer that with more detail, and I'll let them take that if they like. I'm not going to run these next cells. Now I'll just explain what that batch size stuff was about and make the point that it doesn't actually matter. The idea with the batch size is this. What if I, instead of doing one step at a time of the game, is there any benefit to actually doing, let's say, 10 at a time? Now that wouldn't look so great for graphing purposes, but if I'm just doing this computation in the back end somewhere, is it better to do it that way? And it turns out if you study this code carefully, and the numbers confirm it here, it actually doesn't matter because, again, changing the number of calls inside, whether I'm calling game 10 times to step or 1 time to step 10 times, it doesn't actually change the profile of the parallelism of the application. So that's actually not beneficial, and these numbers are just confirming that they all average to about 3.1 or something. Now, if I was doing like, expensive network calls or something like that, where you typically do want to do batching, then you would see a difference. But the way things are built, especially on a single node like this, you're not going to see any benefit from batching, but the hook is there. Mostly because I wanted to prove to myself that it really was the case. Okay, so now we have some exercises. We actually got through that one a little bit faster, and I think we'll take a little time to do this, and then we'll probably skip on to the Ray multiprocessing notebook to finish for the day. But let's talk about these exercises. Okay, to simplify things, let's imagine we have a little counter class, counterculture class, something. Every time I call next, it's going to increment a counter and it'll return the new value. Pretty basic, but it's an example of state. So I declare one that's not using Ray, and it just does the usual stuff. Now there's also I'm going to have a global, or at least an instance level pause value, so I can just wait, for some period of time. And then I can wrap this with Ray by subclassing and create a Ray version as well. So we'll play with this a little bit. Then I've got a couple of functions to just test this out. Now this one is going to be totally synchronous, where I'm going to have some number of counters of instances of these objects, and I'm going to go through them and construct them first. That's what this line is doing that I highlight. And then once they're constructed, I'll iterate through them again, and for each one, I'll just stop at each one and I'll count up to whatever count2 is. Count2 is some integer, 100, 1,000, whatever. And just keep calling next on it, and then I'll move to the next counter and the next counter and so forth. And then when it's all done, I'll calculate how long this took. So once, as you can imagine, this will be all in one thread, all in one CPU core. The Ray version is going to leverage some of the things we've learned already, where I'm going to construct these things, and this comes back immediately. So I'll immediately have num counters of actors. I'm going to do the same 2 nested loops to call next, but these are asynchronous calls, right? So these 2 loops will finish really fast. And in fact, if I didn't do this ray.get, I would get very misleading numbers, because I would basically say, all right, just go do the work. I'm going to say I'm done, even though you might still be out there doing the computation. So when I put in this blocking call, even though I'm throwing away the result that ray.get returns, I'm forcing it to finish. And that will tell me if, that'll give me a more realistic performance number. The idea, though, is that hopefully, primarily because I'll have some n number of these counters running in parallel, that they will actually move a lot faster through this data than this non-Ray version. And as a matter of fact, here's a little exercise that just occurred to me. You might try switching these loops, like do the for n in range loop first, count2 that is, and do the once, and for a given count value, then do the num counters and see if that makes any difference. It might actually have a slight performance impact if you flip the sense of these of the nesting of these for loops. Okay, anyway, let's run this. Oh, forgot to evaluate the cell, I think. Here we go. That's interesting. Name counter is not defined. Oh, maybe I didn't do this one. Let's do this. Yeah, I think I forgot to do those 2. Yes, okay. I love it when a live demo fails. So look at the times and look at the number of counters and the pause times. So for these 0 pauses, you know, it's like it's sub-millisecond. You know, it just rips right through very fast. Kind of a good lesson, actually, that if you really have something that's very tight and very fast at a microscopic scale, make sure you do that as much as you can and don't impose a lot of overhead, like calling something like Ray. But as soon as we start pausing, you know, simulating expensive calculations, then we're basically scaling linearly. So with a pause of 0.1 seconds and 4 counters and counting to 10, it takes 4 seconds. You know, 0.2 pause, 8 seconds. Hopefully you know what's going to happen here with Ray. It's actually going to be effectively flat, except for these warnings. In terms of the counting, it'll actually won't matter how many counters we have. The numbers will be more or less around 2 seconds. So we did achieve parallelism like we wanted. Okay. Actually, I won't even run this next cell. Let's just look at the output from this one. What you'll notice is, so these are alternating, not Ray and Ray, not Ray and Ray. Again, with 0 pause, there's a lot of overhead that Ray is imposing, and it's actually detrimental when we have something that's so fast as just incrementing a counter and there's no delay. Once we add even just 0.1 second delay, then the numbers get closer. But notice that the Ray values always stay just a bit higher for this level. And that's because we really are at a fairly small regime. We really aren't doing anything that compute expensive. And the Ray overhead for Ray is just a little bit larger, at least in this environment. If we increase these numbers, especially, well, I forgot to mention, we're only doing 1 counter here. We're not actually getting any benefit from Ray. What we're actually measuring here is just the overhead of Ray. Apologies for the sound outside. I live near a hospital, so that's probably an ambulance. So let me just say that again. We only had 1 counter, so we really weren't getting the same benefit that we got up here when we had multiple counters. So we're just really measuring the overhead of Ray, which is pretty small, but you know, you would want to pay attention to this. If you weren't actually getting any benefit, then don't use it. All right. And this one is also, what if we take the pause time down really small? You know, when is there a crossing point when we actually do get the benefit of using Ray, or is it always going to be to our disadvantage? And on these nodes, it's actually not very good. We're still going to be more expensive to compute with Ray than not. I think this would be better if I use more than 1 counter. So let's just plot this and move on. I'll actually show you a better plot on a more realistic machine. What you can see here is that there's a pretty constant overhead for Ray versus non-Ray. And you see that in my other notebook over here. This is again running on my laptop. Hopefully it's still working. But it's more or less the same. If we click on another run, kind of the same behavior, a little bit noisier down here for Ray overhead, but the trend is the same. Let's go back to this. And basically that's it. So really this wasn't much of an exercise. It was more about just exploring the overhead of actors and when you get benefits and when you don't. All right. Let's take a pause for a second. Are there any questions about actors or tasks for that matter? You can put those questions in the Q&A panel. I think we might have enough time to do the next 2 notebooks. The next one is actually really short, and I'll give you a little bit more background, and then we'll come back and finish with number 4. So let's do that. What this does is it steps back from all the exercising and evaluating stuff and takes a look at how we got to Ray in the first place. Ray is effectively a response to 2 big trends. This is a plot of the growth in size of neural networks in the last, we've kind of cut off the years here, but it's the last like 5 or 6 years. They've been growing about 35 times every 18 months. By comparison, Moore's law grows about 2 times every 18 months. This is a log plot on the left, so it's a straight line when you have exponential growth. So what that means is that if we're going to try to keep up with reasonable compute times for training these massive networks, we're going to have to go parallel. There's no way around it. Now, the other problem is, well, it's not a problem. The other trend is that more and more people are using Python because of its, it's become kind of the de facto tool of choice for machine learning, data science, that kind of stuff. So the last 5 or so years has seen enormous growth and interest in Python. So that means that we need, and that's what the center bullet is for, we really need a robust yet easy to use way to write distributed Python. And that's really the motivation for Ray, is to address that goal. The other factor about this, though, and this is really kind of what ultimately tipped the team at Berkeley to start creating Ray, is that this is a chart that's kind of showing all of the different sorts of tasks that you might do in a typical data science environment. Not all of them, but a lot of them. Some of the tools you might use, everything from ETL and converting data into features that you can do training with, handling string processing, doing hyperparameter tuning, which is where you find the optimal model structure. That'll be the subject of the next Ray Summit Connect in June 10th. Once you've found that optimal architecture for your model, that's like these neural network architectures, then train the model on data. When you get into reinforcement learning, you're running simulators. They're entirely different sorts of compute models. Like a game engine is a lot different than, like processing a billion records that all have the same schema. Once you've trained your models, you might need to serve them in some way. So there's quite a diversity of requirements for compute and also for memory access patterns. And that kind of led people to realize, you know what, we really need something that's fundamental, that's low level, that gives us the kind of flexibility to write short, fast, long running, distributed, whatever kind of tasks we need. Also manage bits of state in complex object graphs that don't necessarily fit like a typical SQL relationship. And that's what Ray was designed to do. So if we repaint that picture, we get something like this, where Ray aims to be the core framework that could be used to address all of these areas. And today we have several high-level libraries that work on supporting the specific use cases. You may not even touch Ray, the API we've been learning today, if you're working in some of these high-level libraries, like Tune for hyperparameter tuning, Ray SGD for stochastic gradient descent, RLib for reinforcement learning. That'll be the subject of our next training event, or Ray Serve for serving. And we'll cover the other 3 libraries actually in the month to follow, which will be July, I forget the exact date, like the 25th or something. So if you're doing data science, and you're doing some of these higher level things, you may not actually use Ray that much, a little bit more with Serve perhaps. If you're writing a game simulator, you probably would need Ray for working with RLib. But if you're just doing distributed Python, then you might need Ray a lot. And there's a little bit more about these things and then links that take you to more information if you want. Okay. Someone is asking a very interesting question here, which is, what about using Ray in Java? And is this the right form to ask? It's always the right form to ask. There's never wrong questions, there's just bad answers. But hopefully the good answer is that yes, there actually is an emerging API for Java with Ray as the kernel. It's somewhat experimental. I believe we have information on the ray.io site about it, but if not, you can send us email like academy@anyscale.com, and or check out the Ray Slack, and we'll be happy to give you more information about this thing. So people are starting to work on that. Let's see, so let me mark that done. Thank you. And someone's also asking, where can I download the crash course and run on my laptop later at my own pace? The link was in the email that was sent to you, but if you've lost that email or didn't get it for some reason, just go to GitHub, search for the Anyscale account, and then look for Academy. That project has everything that we're looking at today, so you can do it that way. So again, GitHub, it's actually github.com/anyscale/academy, in fact, is the URL. Okay, so we have 25 minutes or so. So for the last period of time, why don't we go through this multiprocessing with Ray lesson. This is the one that explores how you can actually leverage Ray in existing Python applications, even if you're already using some other multiprocessing libraries. And I think that'll be a good place to end for the day. So specifically, we've implemented Ray equivalent versions that use the same APIs as multiprocessing.pool and joblib. Joblib is really popular in the scikit-learn world. Also, we've integrated with Async I, so you can actually use Async I as an alternative syntax for some of the things we've been doing with the Ray API. Why would you replace these other APIs? Well, all of them are limited to a single machine. You know, they're basically designed to properly leverage the cores in your machine by using multi-threading or even separate processes. And Ray can do that for you as well, but it's not limited to a single machine. So just by making these changes, now you can scale to a cluster. So that's the idea. Okay, let's do some imports as we've done before. We'll run that script to verify that we're actually running Ray already. All of this should work fine. We'll initialize Ray in our local process like we've done before. Once again, the local version of the dashboard URL. And let's now talk about these two APIs. The links here, the docs link go to the original libraries in the Python or other ecosystems, and then the Ray docs that describe how to use the Ray versions are these Ray links. Oh, by the way, I didn't mention this earlier. Some of you may have noticed that these tables are right aligned. Extremely annoying. Supposedly this bug was fixed in Jupyter, but it's still happening. So apologies if you find that as annoying as I do. All right, anyway, let's talk about multiprocessing.pool first. Very simple to make the change. You just change the original import statement, which is this first one, to this one, which uses the Ray version instead, and then your code will magically work. So if we have a little simple example here, and all it does is it calculates from 1 to 100, or actually 0 to 99, but it's using multiprocessing.pool, but the Ray version instead of the Python version. So very easy to make this change. I mentioned joblib as part of scikit-learn. If you're starting to go ahead, warning, do not evaluate this cell on these nodes. This will never finish. This is actually training a machine learning model. So do not evaluate this. I'm gonna have to change this to something that's actually tractable, but don't evaluate this cell. But if you want to do the others just to make sure that they compile, that's fine. But once again, the key one is this last bit here. We set up a NumPy model and all this stuff. This right here is NumPy is, scikit-learn is using this joblib multiprocessing system under the hood. We're just going to replace it with the Ray version, and then it'll just run. Excuse me. Okay, I think I did that one already. I will not evaluate that cell, or I'd have to start my notebook over. Oh, by the way, if you need to do that, if you click this circle up here, then it'll ask if you want to restart the kernel. Obviously, brute force. The problem is that if you need stuff that you've already run, you have to go back and do all the cells that you need for subsequent work. So it's only a last resort. Let's talk about Async I. This is an API that a lot of you may not be that familiar with, but it's basically the model of coroutines where you can suspend work that you're doing, let other work proceed, and then come back when something is available that you need. So it's a different model of concurrency. And we don't actually replace Async I, but we integrate with it in Ray. So let's look at how that might work. So I'm going to import Async I, and I'm going to define an actor called async that's just going to basically print some stuff and sleep. And notice that this async keyword is here, which allows it to be invoked multiple times in the event loop at the same time. There's an important thing going on here, and that is, I said earlier that the normal actor model, it's very thread safe, so while it's processing one request for work, it won't do anything else, and that's for thread safety. This actually breaks that, so, but it does so deliberately. Be very careful if you use this when you're mutating state, because you could end up corrupting state. So just use this with caution. but it's a good way for very fine, to achieve very fine-grained currency. That's interesting. I don't know what happened there, but so I imported Async IO, I defined the actor, I instantiated it. Let me just do this. You can split a cell, by the way, with Control-Shift-Dash, and that's sometimes useful if this worked, but you're not sure what's wrong with this one, and maybe they just I needed to wait longer. Let's see if it works now. Not sure what's wrong with this. All right, well, I've got a bug here that I'll have to fix later. Anyway. You can also do this with tasks, though, not just actors. So if we define some task, the normal Ray way to work with this would be to call remote and then wait on it and then maybe get the result when wait returns. I very simplified the idiom that we saw earlier. Let's see, this is still running, it says. So I'm not sure why that's doing that. But here's the alternative syntax you can use with await syntax. And you can just say await on some task that's running remotely, and then you can use async io.await, that method, to actually retrieve the value. And something seems to have locked up. It might have been something in here that got messed up. So I won't evaluate any more cells in here. I'll just mention a few other things. Here's another example of using async and await together in an actor. And rather than try to get that to run, which apparently isn't going to happen, I won't evaluate that now. There is another useful feature, though, that is worth calling out. This is general. It's not limited to asynchronous actors. Sometimes when you instantiate one, you might want to change the parameters that were declared when it was declared with remote. So what I mean by that is this. There's a list of parameters you can actually pass to the Ray.remote decorator that configures things like, this thing needs 3 GPUs, or I only want it to be run 5 times and never more than that kind of stuff. You can find the information about this in the Ray documentation. Sometimes you want to set global properties for an actor, but then specific properties for an instance. And this, async actor.options with, here I'm setting max concurrency equals 3, and then .remote will create a customized instance of this actor. And if we could run this, we'd see that it runs with parallelism of 3. All right, something went wrong up here. I'm not sure what that was. I'll try to debug that to make sure this works for you. The advantage of checking out the Git repo is that I will be pushing updates, and so you can get, you can pull down changes as they're developed. All right, someone asked a question here. If time permits, and we do have more time, please touch upon a bit about operational aspects of setting up, managing, and running the underlying Ray cluster. If we have a bunch of VMs, can I just use Ray multiprocessing to fan out my existing PY3 daemons across them, or additional setup is needed? Yes, that works pretty well. We're actually doing something very similar with this environment that you're using today. There's a set of commands. The one that we're actually running when we do that shell script at the beginning is ray space start space dash dash head. That creates the head node, sort of the bootstrap node. And then when you start you start Ray with the same command on other machines. Instead of saying dash dash head, you actually pass the address and port that's printed by the head command when it runs. I can probably demonstrate that to you. Let me do this. We're basically done, so I'm going to go ahead and stop Ray and then restart it. And the way to do that is I come back to the launcher, click a terminal window, and now I'm actually in the head node. And I can see what this prints. So there's a bunch of stuff that Ray space dash printed about what's running. If I do Ray stop, it will shut down. And kernel restart, wow, that's interesting. So it crashed a lot. If I go back over, let's just pick one of these. Actually, I'll do this one. Now if I go back up here and run, where is it? I think I overshot it. Here it is. So if I run this script now, what it should print is the full output, and here it is. This is what you would normally see when you print out, or when you start a head node in particular, it gives you this line. This is what you would use on all the other nodes to tell them, all right, start up, and here's the address to go out and reach that head node so that you can set up the cluster. There's a Redis password. We're actually using Redis behind the scenes for coordinated metadata management. And once you've done that, then you can set up your cluster any way you want across your VMs, and then it will just work. So if I had done that, as you described in the question, then when I was doing Ray stuff down here, like initializing with auto and so forth, it would span out all that work across the cluster. So it's actually pretty simple. There are some details you can finesse about resources and where they're located, but for just a bunch of worker VMs, it's actually pretty straightforward. And something like this. Now, actually, we didn't pass this Redis password. Since you're seeing that, we didn't use that here. And that's because this happens to be the default. You can actually configure a custom password, which is recommended in production, but it just use the default, so I didn't need to specify it in this case. Okay, we're actually, I think, probably out of time to go through the rest of these lessons, but what I would do is encourage you to try this number 5. This was kind of my favorite one in a way to play with, because maybe it was because I didn't know a lot about parallel iterators before I started, but you can get a sense of how powerful they are. And I actually implemented word count in this thing. If you ever wrote a word count in like MapReduce for Hadoop or wrote it in Spark, it's kind of an interesting twist to do it in parallel iterators. I won't claim that it's an equivalent to the flexibility of Spark, and in particular, it's missing group by, but there's a lot of cool things you can do with it nonetheless. This notebook goes into a little bit more detail about those options you can pass when you're initializing your local instance, the options you can pass to Ray.remote. So that would be interesting to skim through to get a sense of what you might want to tweak there. And I do go into the Ray command, the CLI command, a little bit more in this course or lesson. I have to say that this one is pretty incomplete, though. I'm going to expand this a lot. There's a lot more that isn't covered. And I'm very grateful for everyone attending. Actually, there is one slide I have here to show you at the end. Send us feedback or questions or concerns at academy@anyscale.com. There is a tutorials channel on the Ray Slack. If you're interested in Ray, that's the best place to go for support. And in particular, this channel is good for the tutorials. And I'm really grateful for you coming, and I hope to see you at the next event. So someone asked the question, is it possible to place breakpoints in Ray programs? There's actually a developer mode that forces everything to run in a single process. And that's the nicest way to do debugging with any sort of debugger you want to use. If you look at the advanced material as well, there's a really nice profiling feature, especially for actors, that's a good way to find bottlenecks. Not the same thing as breakpoints, but look at the ray.io website and then the documentation, and you'll find information about debugging Ray programs. Again, the easy way is to force it to run single-threaded so that you can just set breakpoints and know exactly what's going on.